Welcome back, everyone, to the deep dive. Today, we're going to try to wrap our heads around something pretty complex, quantum mechanics.
Oh, yeah.
But don't worry, we're not going to get bogged down in equations and all that super technical stuff.
Right.
We're going to focus on the big ideas,
Yeah.
the really mind-bending stuff that makes you question everything you thought you knew about reality.
Yeah, exactly. It's more about the concepts, getting a feel for how the quantum world works.
Exactly. And to guide us on this journey, we have a really interesting essay to work with called Quantum Mechanics Basics for Beginners. Easily explained.
Catchy title.
I know, right? You'd think quantum mechanics and easily explained don't really belong in the same sentence. But the author, Jurgo Schneepat, actually does an amazing job breaking it down.
Yeah, he really does. He uses these great analogies and thought experiments that make it, you know, actually understandable.
So our mission today is to take what Schneepat lays out and really dive deep into it, explore the key concepts, and, try to make sense of this weird, wonderful world of quantum mechanics.
Sounds like a plan.
So let's start with the basics. Why should we even care about quantum mechanics? I mean, it sounds like something out of, Star Trek or something.
Well, it might sound like science fiction, but it's actually the foundation of so much of our modern technology.
Really? Like what?
Well, think about computers, lasers, LEDs, even medical imaging technologies like MRI. They all rely on the principles of quantum
Oh,
mechanics.
wow, I had no idea. So it's not just some abstract theory, it's actually impacting our lives every day.
Absolutely. And that's why it's so fascinating to understand because it's not just about equations and particles, it's about the very nature of reality itself.
Okay, so I'm intrigued. But where do we even begin with something this complex? Maybe we should start by going back in time, to the origins of quantum mechanics.
Good idea. Snaphat talks about this in his essay. It all started in the late 19th century with scientists struggling to explain something called black body radiation.
Black body radiation, what's that?
Basically, it's the light emitted by heated objects. Like imagine a piece of iron as you heat it up, it starts to glow first red, then orange, then white.
Right. I've seen that before, like in a blacksmith's forge.
Exactly. Now, the problem was that classical physics, the physics of the time, couldn't explain the exact pattern of light emitted by these objects. They called it the ultraviolet catastrophe.
Catastrophe. That sounds dramatic.
It was a big problem because their calculations predicted that the amount of energy emitted at high frequencies would be infinite, which obviously doesn't make sense.
Yeah, that's definitely a catastrophe. So how did they get out of this mess?
Well, a German physicist named Max Planck came up with a radical solution in 1900. He proposed that energy wasn't continuous like a smooth flow of water, but came in tiny, discrete packets.
Packets of energy, like little bundles.
Exactly. He called these packets quanta, and that was the birth of quantum mechanics.
So instead of energy flowing like a river, it's more like a stream of individual droplets.
That's a great analogy. And this idea that energy was quantized, it was revolutionary. It completely changed our understanding of how the universe works at the most fundamental level.
Wow, so Planck really shook things up. And then didn't Einstein come along a few years later and take this idea even further?
He did. Schneepat talks about Einstein's famous Annus Mirabilis, his miracle year of 1905, when he published a series of groundbreaking papers.
One of those papers was about the photoelectric effect, right? Where light shining on a metal can knock electrons loose.
Exactly. The photoelectric effect couldn't be explained by the classical wave theory of light. But Einstein, using Planck's idea of quantized energy, proposed that light itself was made up of particles, which he called photons.
So light is both a wave and a particle. That's kind of confusing.
It is. It's one of the first big mind-bending concepts you encounter in quantum mechanics. It's called wave-particle duality, and it basically means that light can behave like a wave or a particle depending on how you observe it.
So it's like light has a split personality. Sometimes it's a wave, sometimes it's a particle.
No way. And Einstein showed that the energy of a photon was directly proportional to its frequency, which explained perfectly how the photoelectric effect worked.
So Einstein took Planck's quantum idea and ran with it.
He did. And his work really solidified the foundation of quantum mechanics, paving the way for all the incredible discoveries that followed.
So we've got quantized energy and light as both wave and particle. What comes next in this quantum story?
Well, the next big chapter is about the atom itself. In 1913, a Danish physicist named Niels Bohr came up with a new model of the atom.
I remember learning about the Bohr model in school. It's the one with the electrons orbiting the nucleus like planets around the sun, right?
That's the one. But Bohr's model wasn't just a pretty picture. It was based on some radical ideas that combined classical physics with quantum mechanics.
Okay, so how did he incorporate quantum ideas into his model?
Well, he proposed that electrons could only exist in specific energy levels within the atom. They couldn't just orbit anywhere. They had to be in these discrete orbits or shells, kind of like those quantized energy levels Planck talked about.
So it's like the electrons are restricted to certain lanes on a highway.
Exactly. They can't just swerve all over the place.
Hmm.
And when an electron jumps from a higher energy level to a lower one, it emits a photon of light with a specific energy.
And that energy corresponds to a specific color of light.
Right, exactly. That's why different elements emit different colors of light when they're heated, because their electrons are arranged in different energy levels.
It's pretty cool. So
Wow.
Bohr's model explained those colorful spectral lines we see when we look at light through a prism.
It did. And it was another huge step forward in our understanding of the atom and how it interacts with light.
Okay, so we've got quantized energy light acting like both a wave and a particle, and electrons jumping between energy levels in atoms. It's a lot to take in, but I'm starting to see how these pieces fit together.
It's a lot, but it's also incredibly exciting because we're starting to unravel the secrets of how the universe works at its most fundamental level.
And we're just getting started. Schneppad goes on to talk about even stranger and more mind-boggling developments in the 1920s, things like wave mechanics, the Schrödinger equation, and the Copenhagen interpretation.
Yeah, things get really weird and really interesting from here on out.
I can't wait to dive into that. But for now, let's take a quick break, and we'll be back in a moment to explore the even deeper mysteries of the quantum world. Okay, so we're back and ready to plunge even deeper into the quantum rabbit hole.
Buckle up, things are about to get really weird.
I'm all for it.
Yeah.
So we left off talking about Bohr's model of the atom with those electrons jumping between energy levels.
Yeah, that was a big step forward, but the story doesn't end there. In the 1920s, things got even more interesting with the development of wave mechanics.
Wave mechanics, that sounds intriguing. What's that all about?
Well, it started with a French physicist named Louis de Broglie. He had this crazy idea that if light could act as both a wave and a particle, maybe matter could too.
Hold on, you're telling me that things like electrons, those tiny particles that make up atoms, could also behave like waves?
Exactly. It was a radical idea, but it turned out to be true. De Broglie proposed that all matter has a wavelength associated with it.
So it's like everything in the universe has this wave-like nature, even things we normally think of as solid particles.
That's the idea. And this wave-like nature of matter, it has real consequences. It explains things like why electrons and atoms can only exist in the specific energy levels we talked about.
Okay, so instead of picturing electrons as tiny balls orbiting the nucleus, we should imagine them more like waves.
Yeah, it's more accurate to think of them as standing waves, kind of like the vibrations on a guitar string.
I'm trying to picture that. So the electrons are like these waves vibrating around the nucleus, and only certain vibrations are allowed.
Exactly. Those allowed vibrations correspond to those specific energy levels. And this wave-like nature of matter, it led to the development of one of the most important equations in quantum mechanics, the Schrödinger equation.
The Schrödinger equation. That sounds intimidating.
It's a pretty complex equation, but basically it describes how the wave function of a particle changes over time.
Wave function. What's that?
The wave function, it's like a mathematical description of the state of a particle. It contains all the information we can possibly know about the particle, like its position, momentum, and energy.
So the wave function tells us everything about a particle.
Well, not exactly. It tells us the probabilities of finding the particle in different states. For example, it might tell us that there's a 50% chance of finding an electron at location A and a 25% chance of finding it at location B.
Wait a minute. So we can't know for sure where the electron is. We only know the odds of finding it in a particular place.
Exactly. That's one of the most mind-blowing things about quantum mechanics. It's fundamentally probabilistic. We can't predict with certainty the outcome of a measurement. We can only talk about probabilities.
That's pretty different from classical physics, where we're used to things being predictable and deterministic.
It is. It's a big shift in thinking. But this probabilistic nature of quantum mechanics, it's not just a theoretical quirk. It's been confirmed by countless experiments.
So it's like the universe itself is playing dice with reality.
In a way. And this brings us to another key concept in quantum mechanics. Heisenberg's uncertainty principle.
I have heard of that one. It's something about not being able to know both the position and momentum of a particle with perfect accuracy, right?
That's the gist of it. It basically says that the more precisely we know the position of a particle, the less precisely we can know its momentum, and vice versa.
So it's a trade-off. The more we know about one property, the less we know about the other.
Exactly. And this uncertainty, it's not due to any limitations in our measuring instruments, this fundamental principle of nature.
So it's like the universe is putting a limit on how much information we can know about a particle.
Yeah, in a way, it's like there's this inherent fuzziness built into the fabric of reality.
Okay, so we've got wave functions, probabilities, and uncertainty. It's all starting to feel like we're venturing into Alice in Wonderland territory.
I told you things were going to get weird, but it gets even weirder. Schneppet also talks about this idea called superposition.
Superposition. What's that?
Well, it's related to the idea of the wave function. Remember how the wave function describes the probabilities of finding a particle in different states?
Yeah.
Well, superposition means that a particle can actually be in multiple states at the same time until we measure it.
Multiple states at once. How is that possible?
It's one of those things that's hard to grasp with our classical intuition, but the math and the experiments, they all point to the fact that superposition is a real phenomenon.
Okay, so give me an example.
Mm.
How can something be in multiple states at the same time?
Think of a coin spinning in the air. Before it lands, it's neither heads nor tails. It's in a state of both possibilities simultaneously.
Okay, so it's like the coin is in a superposition of heads and tails until it lands, and then it collapses into one definite state.
Exactly. And it's the same with particles in the quantum world. They can exist in a superposition of multiple states until we measure them, and then the wave function collapses, and we get a definite outcome.
So it's like our act of observing something forces it to choose a specific state.
In a way. And this idea of superposition, it leads to one of the most famous thought experiments in quantum mechanics, Schrödinger's cat.
Ah, yes, I've heard of that one, but I'm not sure I fully understand it.
Well, imagine a cat trapped in a box with a device that has a 50% chance of killing the cat.
Okay, that's already a pretty disturbing scenario.
Now, until we open the box, we don't know if the cat is alive or dead. So according to quantum mechanics, the cat is in a superposition of both states. It's both alive and dead at the same time.
Wait a minute, you're telling me that the cat is both alive and dead until we look inside the box?
That's the essence of the thought experiment. It's meant to highlight the strangeness of superposition and how it challenges our classical understanding of reality.
It definitely does. So is the cat really both alive and dead?
Well, Schrödinger's cat is just a thought experiment. It's not meant to be taken literally, but it helps us visualize the concept of superposition and how it applies to quantum systems.
Okay, so superposition is real, but Schrödinger's cat is not.
Exactly. And this idea of superposition, it's not just a philosophical curiosity, it has real-world implications. It's the foundation of quantum computing and other emerging technologies.
So all this weirdness, it actually has practical applications.
Absolutely. And that's what makes quantum mechanics so exciting. It's not just about abstract theories, it's about understanding the universe at its deepest level and using that knowledge to create new technologies and solve real-world problems.
I'm starting to see why people get so passionate about quantum mechanics.
Right.
It's challenging and mind-boggling, but also incredibly rewarding.
It is, and we're just scratching the surface. Schneppet goes on to talk about even more mind-bending concepts like entanglement and the many worlds interpretation.
I can't wait to dive into those. But for now, let's take a moment to digest all this amazing information about wave mechanics, superposition, and the uncertainty principle.
Yeah, it's a lot to process, but once you start to wrap your head around it, it's truly awe-inspiring.
Okay, so I think we've covered a lot of ground here.
Yeah, we've gone through, quantization,
With particle duality,
the uncertainty principle.
superposition, entanglement.
It's a lot.
It is, and it's all pretty mind-blowing.
It really makes you think about what reality actually is.
Right, like if things aren't really defined until we observe them, what does that mean for our understanding of the universe?
That's the big question, isn't it? It's what physicists and philosophers have been debating for decades.
Schneppet touches on this in his essay too, this whole idea of the observer's role in shaping reality.
Yeah, he talks about how quantum mechanics challenges our classical notions of objectivity and determinism.
It's almost like we're participating in the creation of reality just by observing it.
That's one way to look at it, and it's definitely a profound implication of quantum mechanics.
It is. And it raises all sorts of questions about consciousness and the nature of reality itself.
Yeah, it really takes us to the edge of what we know and forces us to confront the limits of our understanding.
But that's what makes it so fascinating, right? The fact that we're still grappling with these questions after all these years.
Yeah. Absolutely. It's a sign that we're on the right track, that we're pushing the boundaries of human knowledge.
And who knows what amazing discoveries are still waiting to be made.
Yeah, that's the beauty of science. It's a journey of constant exploration and discovery.
Well, I think we've given our listeners plenty to think about today.
Yeah, I hope they're as amazed by quantum mechanics as we are.
I'm sure they are. And if they're eager to learn more, I highly recommend checking out Yorgo Schneppet's essay, Quantum Mechanics Basics for Beginners. Easily explained.
It's a great resource for anyone who wants to delve deeper into these mind-bending concepts.
We'll have a link to the essay in the show notes, along with some other resources for further exploration.
And as always, we encourage our listeners to keep those minds open and keep questioning everything.
Because who knows, maybe one of you will be the one to unlock the next great mystery of the quantum world.
Yeah, the future of quantum mechanics is full of possibilities.
Thanks for joining us on the deep dive, and we'll see you next time for another fascinating exploration of the universe and beyond.